Start. So yesterday we started sequential modeling, sequential circuits modeling. As I told you, behavioral level is very supportive for the what? Sharp steering. Okay. Start one more time. Screen to okay. Yeah, present. వాళ్ళకి వస్తుందా?
సార్ మాకు కనబడుతున్నది.
Okay. Wait a minute. Okay. Yesterday I told you how to design the latches, okay, and PIPLAF also. PIPLAF especially for the DPIPLAF, synchronous clear and asynchronous clear. Okay, synchronous clear and asynchronous clear. The difference is what? So in the sensitivity list, you need to what? Include positive edge clock, only positive edge clock. This is the sensitivity list. Where is this is the sensitivity list. Sorry, this is the sensitivity list, positive edge clock. And here is, if clear is not 1, that means if the clear is 0, so everything should be clear. So else Q is equal to, this is the simple DPLOF. And in asynchronous clear, you should take, I think in asynchronous mode, what happened? The clear is given to all the PIPLOFs or this PIPLOF at the same time. Okay, suppose here is only we are talking about the single PIPLOF. And the PIPLOF has 2 control signals. One is the clock, one more is the, what is that? What is that? Clear. Okay, both should be included in the sensitivity list. So this is the sensitivity list. We have 2 things. One is the 2 signals. One is the positive clock and one more is the negative edge of the clear. Okay, but the statements are same. whatever the behavioral statements, that is if clear is 0, Q is equal to 0, otherwise Q is equal to D. This is a simple dbplof. So this is the dbplof with asynchronous reset. So this is the dbplof. The entire circuit diagram is the dbplof with asynchronous reset. See the schematic. This is a schematic. Okay. I think this is a circuit diagram. This is a schematic. This is the what? So I think characteristic table, excitation table. So which means what? This is the reset, and this is the clock. This is the D. If you see the first row, what happened whenever reset is 0? Okay, irrespective of the clock, and input Q is 0. Q is 0. Okay, irrespective of the clock and data. Okay, and if you see the next row, what happened? If the reset is 1, okay, what happened? Well, with the clock change, that means positive edge clock, that is upward direction, means from 0 to 1. Here you see symbol. What is there? Arrow mark is upward, which means positive edge. Nothing but change of the clock from 0 to 1. Clear? If the D is 0, Q is 0, as is on dbplof main main functionality is same thing. The input should be appear at the output. So simply, whatever the input, that should be appear at the output. That is called the dbplof. So some delay will be there. Okay. So next one is see, reset is equal to 1 and clock is equal to again there, then D is equal to 1. So when D is equal to 1 again, because already reset is 1, reset 1 means it is not activated. Okay, reset 0 means what happened? So I think everything will be reset. So whenever the clock is equal to, I think positive edge, then D is equal to 1, then Q is equal to 1. So these are the rows. And see, this is the schematic. In this, so this is the data input, this is the clock, this is the reset. See, the reset is having the bubble, which means what? So whenever it is 0, it is activated. Whenever it is a 1, it is not activated. So whenever it is a 1, the reset will not work. Whenever the reset signal is 0, the reset will be working. What is the intention of the reset? Reset intention is simply what? Make everything is 0, whatever the earlier data. Is it clear? Yes. Now see this circuit diagram. So whenever you are increasing the more signals to the dbplof, I think the circuit requires more gates. See, you know the simple dbplof how it is looking in the earlier yesterday's slides. But today I'm including what? Reset. See, the reset should be given to all the what? Here is reset is given, which makes to 0. And the reset is supplied to here also, which makes to 0. Which makes to 0 means what? So irrespective of these 3 inputs, irrespective of these 2 inputs, sorry, I'm not talking about. See, the reset, whenever the reset is 0, look at this side, irrespective of the other 2 inputs, the output is 1. Am I right? Because if it is an AND gate, whenever the at least 1 input is 0, the output is high. But my point or not? If you take the NAND gate operation, so let us take any number of inputs. Don't bother. If single input is 0, the output is 1. Irrespective of going of the other inputs status. Yes. So this is 1. And the same reset is supplied to here also. So that this is also 1. Okay. Which makes And similarly, the reset is applied to here. So which makes all these settings Q become 0, whatever the previous state. So whenever we are talking about flip-flops or sequence circuits, we must aware of the previous state and next state. We must know the terminology of the previous state and next state. So irrespective of the previous state, the next state becomes what? 0 whenever the reset is activated. Here in this circuit, because of the reset is having a bubble, the reset is valid with the 0. Okay, the reset is not valid with the 0. That means not valid with the 1. I think you understood this circuit. This is a asynchronous reset based DB flip. Got my point? So now we need to write the what Verilog code for this one. Generally, if you want to continue with the earlier knowledge, that is gate level modeling, what to do? So I think so all the gates should be taken as instances, and all the signals must be take care of inputs and outputs and write the code. Okay, but so I already told you that for the sequence circuit design, the best thing is behavioral modeling, so that whenever you are talking about the behavioral modeling, I think you need not be worried about logic circuit. So whatever the number of gates, I think 6 gates are there, 6 NAND gates are there. Some are 2 inputs, some are 3 inputs. We are not worry about them. We don't bother about that. But only the thing is how the circuit is behaving, that you can identify with the what functional table. Okay, got my point? So then we'll go for the, see here is, this is the, this circuit, this code. This is the flip with asynchronous reset. This is not. This is the simple DB flip. Simple DB flip is not having any reset or preset signals. Just is having a clock and D input and output Q. Only 3 signals: input, output, and clock. So because of it is a flip and it is moreover it is synchronous circuit, so definitely there should be a clock. Without clock, it won't be work. So that what to do? So simple signals D and Q and clock is there. That is in the left hand side code. Whereas in the right hand side code is what? For the whatever the circuits we seen in the previous, exactly previous slide. Clear? That is what? DB flip with asynchronous reset. Not clear. So what is the difference between the clear and the reset? So which one is highest importance? So earlier, yeah, here you talk about the clear. So the clear may be synchronous clear and asynchronous clear. So I already told you, asynchronous mode, we must be include the signals, since more signals in the sensitivity list. And moreover, what is that one? Clear makes the clear has upper hand than the other things. So, but here reset I'm talking about. So, is there any difference between the clear and reset? Yes, a lot of difference is there. So, if there is no difference, why you use the 2 things? Why don't you use only single one? Okay. Yeah, need an small exercise. Do it. Check it. What is the difference between the clear and reset? And come with that knowledge in the next class. Okay. Clear? Yeah, you have an anxiety. You can explore in the what? Google. Okay, we'll see. Okay, anyhow. So now this is the time just to discuss about the what? DB flip with asynchronous reset. Okay. So as I told you in the behavioral modeling, we don't bother about whatever the gates and whatever the continuous assessment statements, all the things. Just we should know how the circuit is behaving, how the data is flowing, based on that, how the algorithms are working. Okay, how the architecture can be implemented. Based on that, you can write. Okay, this code. Yeah, anyhow. So first line, module space. I forgot the space, or a space is there. Yes, space is there. My what object name is DFF, and open the brackets. Keep all the signals all the signals or ports in the brackets. Then in the next line, declare the ports, which are the inputs and which are the outputs. And don't forget that in the behavioral modeling, all the outputs are what? Registers. Okay, so that output port name is what? Q. It must be again register, and input is D clock reset. As we discussed in the latch, I already stressed about the reset, the importance of the reset and priority of the reset while while we discussed in the latch design. Whenever you are including the reset, which one has highest priority? Reset has highest priority. So generally in the sensitivity list, if the clock is there, so based on that, we enter into this one. After that, check the reset. Check the reset. If the reset is 0, so without doing of anything, just make it without checking of the inputs, without knowing of the input, you can say, so Q is equal to 0, 1 bit binary value. See the first line after always block, in the always block, the first line is if what? Negation of RST, Q is equal to spaces, maintain the space or go to the next line, don't worry. And Q is equal to what? 0, 1 bit binary value 0. Otherwise, means what? If the reset is not 0, means what? Reset is deactivated. Now the next state depends on the input, not the previous state. So that's why in the dbplov, in excitation characteristic equation, I think you must know about the characteristic equation, excitation table, all must be known. So because these are the pandas, you may already you studied in the UZ class or another coursework DLD. Excitation table, characteristic equation. What is the characteristic equation of that? dbplov. Qt plus 1 is equal to D simply. The next state is equal to input only. Okay, so that's why else Q is equal to D. End module. Do you have any doubt? Then write down, note down this one. So yeah, I think this circuit is not enough, not required, but these two are enough because we don't want about this one, because we are not doing the modeling in gate level. So that so with this we can understand only the thing why this is required is because the reset is what type of, that is active for 1 or 0. Here the reset is active for 0. Yeah, if you remove that bubble, the reset is active for the 1. Clear? Yeah, note down these two things. Then go to the code, note down it. So otherwise take a snap. You can note down later. Better. Okay then. Yeah. Yeah, note down the code also. Okay, then we'll move the next slide. So I think the same thing it is also. Just the same thing. Here, a small mistake is there. Yeah, here you forget about this one. Here. Listen, always the difference I'm going to tell you. Always at the rate of positive edge of the clock or negative edge of the reset. Reset is a signal. Reset also signal. It is also just like a clock, but the frequency, all the things will be different. That means clock pulse width is different. So reset is nothing is new for the new apart from the clock. So of course clock is having regular intervals, but reset maybe according to your, you can make it high some duration and make it low for some other duration. There is no periodicity. There is no periodicity, but clock is having periodicity. Okay. So I think you know about the periodicity. That means, so within, after every fixed time interval, it must be resembles the previous thing. Okay. So that is okay. Anyhow, yeah, here positive edge of the clock or negative edge of the reset, it founds anything. Negative edge means what? The reset signal fall from 1 to 0, makes a transition from 1 to 0. That is called the negative edge of the reset. So whatever the, either this signal or that signal happened, enter into this one, enter into this loop. Okay. Here, see, positive edge triggered impulse with reset. Positive edge triggered, same thing. Whatever the same thing, reset, everything, clock, reset, D, Q, all are included. Okay, positive edge clock or positive reset. I am talking about now with positive RST. Positive edge of the reset. If reset is 1, Q is equal to 0. Okay, Q is equal to 0. If reset is 1, Q is equal to 0. Am I right? Else Q is equal to 0. So what is the difference between here and here is, I think you can find whatever the behavioral statements in the always block are non-blocking statements. And here, sorry. And here, the statements are blocking type. Sorry, there is non-blocking type, here is blocking type. Here is non-blocking type, there is a blocking type. That's blocking, is non-blocking. If reset is 1, if reset is 1, here is what happened. If the reset is 1, it is activated. Q is equal to 0. Hello? Class come on, first cap. Nora, another. Sir, I took phone class. Okay. So if reset is 1, no negation. Reset is 1 means active or deactive. Because there is inside, there's positive edge is talking. That's why it's 0. Earlier, it is a negative edge of the clock, negative edge of the reset. It is positive edge. That's why I make it reverse. Okay. And so one more is like this. There are so many things like, there are so many things are there. Earlier, the same. This different. Take a snap. This diagram is belongs to this, okay? But here I use the what? Non-blocking type. So of course that is enough. Name not about this one. Okay. Now JK bluff. D, JK, and T. Generally, these three are important for us. D. What is the importance of the DB bluff? Yeah, the students who are in the online also, they can tell. What is the importance of the DB bluff? Answer the question, everyone. In the chat box also. Hmm? What is the importance of D biplov and T biplov? Generally, D biplov is used in the register design. T biplov is used in the counter design. Counters ki adu vaadtamu, registers ki idu vaadtamu. What is the difference between register and counter? Hmm? Store the information and same information you can get it. But counter is one not like that. It is a counting the events. It is a count the natural sequence or the any other sequence. Natural binder sequence or any other sequence. Okay. Hmm? So here is first one is JK Plough. You can make the T Plough as JK. So generally JK has a small disadvantage, that is whenever J and K both are ones. JK Plough has a one setback. What is the setback of the JK Plough? So if you remember the table, that means both J and K is equal to 0, or J is equal to 0 and K is equal to 1, K is equal to J is equal to 1 and K is equal to 0, and J, K both are 1, 1. Out of all conditions, all combinations, the issue comes with only whenever J and K both are ones. A popular name you already know, that is racing problem. Racing problem means what? There is no stable output. There is no stable output. For one input, you should get one output. But for one input, you get more outputs. More output means, suppose generally for this particular input, the output is 0. But this output 0 becomes 1, then 0, then 1, then 0, then 1. It is changing like this. There is no stability. Okay. And after some time, we are unable to, what is exactly the output? Understand or not? If it is stick to one value, we can say this is the output. If it is oscillating, we could not say the exact one. That is the issue. That is it's changing. We continuously changing the output. That is the issue of the JK Plough. For that, I think to avoid the racing issue, the racing issue comes in only whenever J and K both are ones. To overcome this, generally we have two things in our hand. One is the master slave JK Plough, and another one is what? Yeah, why this is happening means this is happening. That means the racing issue happens. This issue is very serious because of clock is I think what is that one? Clock duration is more if more than the Plough propagation delay. Suppose the Plough propagation delay is 2 nanoseconds, which means to pass the input to the output side or to change the outputs corresponding to the input side for the corresponding inputs, it takes 2 nanoseconds. If the clock is high for the 5 nanoseconds, then within 5 nanoseconds, because of Plough delay is small than, so nearly 2 times, yeah, more than 2 times it is less, it is more. Then what happened? Within this 5 nanoseconds, the Plough can be changed its value more than once. More than once. For one time, earlier it's 0, it becomes 1. For the next, it becomes again 0. Next, it may be changes. Within a one clock duration, because the clock width is more, okay, than the Plough delay, the outputs are toggle more than once. That is the racing issue. To avoid this issue, what to do? We have two things. One is the master slave JK, and another is what? So keep your clock width less than the what? Plough delay. If clock width is 1 nanosecond, If flip-flop delay is 2 nanoseconds, okay, so for the corresponding inputs, output changes. Okay, after that, what clock is already low, so that once the clock is low, I think your flip-flop will not work. So that same outputs are toggling only once. That is the two things you have, but master slave has many issues because it is complex. There are two set of JKs are required. More hardware is required. So anyhow, that is the, but the what is that one slogan is there that you should find the opportunities in crisis also. Am I right or not? It's a very famous quotation. What? Find the search your opportunities in the crisis. Clear? So like that, make this disadvantage as advantage. That is the TP plus. See, so the issue comes only when J and K both are ones. Yeah, tie them, use them. You can name it as a TP plus and use in the counters. Clear? So that is the TP plus. Okay. In the TP plus, see the characteristic equation. So characteristic equation is nothing but the next state. As I told you in the sequence circuit, the next state is equal to function of the inputs and the present state. Outputs kaadu. There is no output here. We should say inputs, present state, and next state. If you take the first equation, characteristic equation, Q of t plus 1, that is called the next state, is equal to Q, previous state, T, input. Yeah, the next state is equal to XOR of present state and the input. Okay, this is the characteristic equation of the TP plus. Whereas JK, if you for the JK means all conditions should take care. That means all in the excitation table, all four combinations will come. If you simplify it, you will get the next state is equal to what? J Q bar plus K bar Q. J Q bar plus K bar Q. Don't say it is a J and Q XR because it is not J Q bar plus J bar Q. It is J Q bar plus K bar Q. Clear? So inputs are here JK, J and K, and next previous state is what? Previous state is Q and A. Q and Q bar, of course. Yeah, Q only we talk about. These are the excitation. So sorry, these are the characteristic equations. So characteristic equation, what it means? That is nothing but next state equations. Next state equations with respect to the present state and the inputs. Got it? Yeah. So JK and T. JK characteristic equation is this, and T characteristic equation is this. So T, you can realize that T, you can implement the T from the JK simply by tying both inputs J and K. Only one case is available there. Whenever these two are tied, the T it can be 0 or 1. Whenever T 0 means both J and K are 0. Whenever T 1, both J and K is 1. Got my point? Yes. See, this is the DV plus. This is the T from the JK. This is the T from the D. The final D symbol is this. So from the D, how can you get the what? T. See, D can be achieved. Sorry, T can be achieved from the D. Both T and Q are both T and Q are XORed. You will get this one. So all the three are what? All the three are TP plus only. But one from the JK, but one from the D, and one is the symbol. Is the clock, Q, Q bar, and T. Got it? Just take a snap. Okay. Yes, next. Yeah, now see T from D. What is the T from D? This is, am I right? T from D. Yeah, what are the signals? Q, T, clear, reset. Include the reset. Include the reset. Yeah, ports are Q output, resistors are output Q, Q is output and resistor, and T and clock and reset are the inputs. Wire DT. So wire is required. We'll see why it is required. Wire because required means here is wire. This is the signal is wire. This is wire. Because we are talking about this and this and this on this and only. We are not talking about this one. So if you take this whole block as one block, then this is the intermediate signal. That's why one wire is required. This is the wire DT. So assign DT is equal to what is the DT? What is this output? XR of these two, T and Q. Okay, so that right here. So assign DT is equal to Q exclusive R of the T. Okay, this is what type of statement it is? Data flow statement. Data flow statement. Continuous assignment statement. Continuous assignment statement. Now, so already you have a DB plug. Already you have a DB plug. So earlier you already designed, that is the DFF is the earlier DB plug. Maybe this or this, okay, or this, you can take anything. So maybe my point of view, this is I use this plug because already I have a DB plug. I have already DB plug. Clear? So here I don't want to write the code for the DB plug. Just I want to generate this signal. So that this is the what? DFF is the what? Instance name. Okay. And this is the signals Q, DT, clock, and reset and end march. The order of these signals must be same as the DP plug. In the DP plug, whatever the order you find, you wrote D, Q, D, clock like this. Suppose if you take this one, then you can change according to that one. Q, DT, clock, reset. Reset should be last. Reset should be last. Otherwise, it can take if you give a jumbling manner, it can understand this is clock is reset is clock like that. Okay, this is the JK plug from DB plug and gates. JK plug from the JK from D and some gates. So okay, module JK plug Q JK inputs and outputs. Write all the ports. So output Q, wire JK, input JK something, and assign JK is equal to, already characteristic equation is here. What? J Q bar plus K bar Q. Yes. Generate that one. Assign JK is equal to this. Now give it to the JK. So sorry, DFF JK1, right? Q comma JK comma clear comma reset. Q same order. So JK generate signal wire clock and reset. They are same positions and watch. Understand? If you want to write, if you want to make it. Okay, I think JK is equal to this one. This is the D. Okay, so I want JK from this. I want JK from this. This is the Q. This is the Q bar. What is the J? J is equal to, JK is equal to, these two are running operation. This is ANDing. Both will be OR. Yeah, this is. What are the inputs? J and Q bar. J and Q bar. This is K and K bar and Q. And Q. Understand? Okay, otherwise, this is the D. If you want JK, take one AND gate, another AND gate, one OR gate. This output is applied D. This is J. This is Q bar. This is K bar. This is Q. Where is Q? This is Q. You can join like this or write like this, no problem. Q bar. You have this D flip-flop. You want JK flip-flop. You want JK flip-flop. Then you can write this code. Yeah, this is a insight. You are using D flip-flop to generate the JK flip-flop operation. Then what happened? Already D is designed or already implemented D, so that you can write this code. Okay. Yeah, no doubt. Okay. Yeah. So functional description of JK. So how can you implement JK directly without what is that one? D plus. Without D. Directly JK you can implement. Clear? So I think module JK underscore F flip J one input, K is another input, clock is one input, and Q not are the outputs. So you can write Q and Q not are what outputs. Okay, and registers Q inputs are JK and clock. Always at the rate of positive edge clock. Okay. Now use the case statements. Case statements. Case JK. If both are 0, 0, first case case alternative is 0, 0. Case expression is Q is equal to Q. If both are 0, 0, Q is equal to Q. Suppose another case alternative is 0, 1. If J is 0, K is 1. What happened? So Q is equal to 0. Reset. Okay. So another case alternative is 1, 0. So then J is 1, K is equal to 0, which means set case. So that Q is equal to 1. Another case alternative is both J and K are 1, 1. Then Q is equal to negation of Q bar. Q means ఇంతకు ముందు Q value 0 అయితే ఇప్పుడు 1. ఇంతకు ముందు Q value 1 అయితే ఇప్పుడు 0. That is called the toggling. AND case and module. This is the JK flip-flop implementation. So this is one type. That is another type. This is direct implementation of JK. That is implementation to the D. See here, there is some note is there. Here the flip-flop is described using the characteristic table rather than the characteristic equation. Characteristic equation and QT plus 1 is equal to J into Q bar plus K bar into Q. Now this is the cases means using of table, excitation table or characteristics table. The case is the, I already told you, case is what type of multi-way branching instruction. Okay, so the case values JK is evaluated and compared with the values of in the list. What happened here? Whatever the case expression, whatever the values inside this bracket will be comparing with this all the cases. Suppose it is matching with this, this is the output. If it is matching with this, this is the output. This is the matching with this. So to whom it is matching, based on that, one of the statement will be clear. So case is nothing but simply comparison. Yeah, that is the flip-flops, D and JK and T. So now I already told you, you can implement that register with the D plus, or without D plus, you can directly implement by using of the behavior. There is there a register. Okay, how many bit register? 8-bit register, because Q size is 8. Q size is 8. Q is a what? Variable, vector type variable. It's a port declaration. The port name is Q and the size is 8 bits. And input size is also 8 bits. Input port name is D. And two more inputs are there: clock bar, clock clear, and set bar. Set bar, set. Okay. Set bar and content. So you can write always in the sensitivity list, include all set, clear, and clock. I think clock, positive edge clock. So negative of the clear and negative of the set. Clear is what? To clear the content. Set is for what? To set any value. For this 8-bit register, suppose 8-bit register value, I can say in the 8-bit register value in decimal, I will tell you. Suppose the value is 20. 8-bit 20 untada? 8-bit 20 untada? Yes, you can define 20, value 20 using of 8 bits. So I want to the next value immediately. I want to set the next value immediately 50. 50 untada? 2 power 8 kada? Untadi. So to set any value, you need the set signal. To clear whatever its value, you need the clear. So if clear is 0, so everything is clear. Q is equal to 0 means all 8 bits are 0. Else if set is 0, a condition raskod Q and 1 set kaakpote. Clear 0 aithe everything is 0. Set 0 aithe everything is 1. Adi condition raskunnam. Else a rendu kaledante. Ante clear 1 undi, set kuda 1 undi, ante register operation jaragali. అంటే ఏమవ్వాలి? Q is equal to D అవ్వాలి. మీరు ఏ ఇన్పుట్ ఇస్తే అదే అవుట్పుట్ లో రిఫ్లెక్ట్ అవ్వాలి. అండ్ సింపుల్. ఓకే, సో విచ్ మీన్స్ this is my register. This is my register, 8-bit register. It has D input, 8-bit D input, and 8-bit output. Q is output, 8-bit. And clock is mandatory, that is a clock. Apart from that, two more values are there. One is the clear, one more is the set. CLR, SET set. Okay, you can say clear, set, clear, CLR, clock, CLK, and D and Q. If both are 0, set is 0 and clear is 0, irrespective of the clock, irrespective of the input, output is 0. If the both are, if the clear is, sorry, small change. If the set clear is, set is 0, clear is 0. 1 minute. If clear is 0, yes, yeah. If the clear is 0 and set is 1. If set is 0 and clear is 1, irrespective of these things, Q is 1. So the conditions are ఉన్నాయి. If clear is 0, output is 0. If clear is 1, set is 1, output is 1. Set is 0. Okay. Next, ఈ రెండు కాలేదు అంటే ఈ రెండు కేసులు కాలేదు అంటే ఈ రెండు 1 1 ఉన్నాయి అనుకోండి. 1 అన్నా, యా 1 1 ఉన్నాయి అనుకోండి. అప్పుడు క్లాక్ 1 అయితే సో డి 0 అయితే, సారీ 0 అయితే క్యూ 0, డి 1 అయితే క్యూ 1. Understand? That is the behavior based on that you wrote this code. Okay. Priority wise, clear this. Okay. Yes. I will stop here. Any doubts? Huh? Okay, Andy. Bye.
Bye, sir.